Hello, my name is Hans Boden. I work at McMaster University in Hamilton, Ontario, and today I'm going to tell you about the Gordon-Litherland pairing for knots and links and thickened surfaces. So before I begin, let me thank the organizers Micah, Sujoy, and Rob for giving me the opportunity to speak. This has been a great seminar series. I've really enjoyed the talks that I've watched, and it's a real privilege to speak about collaborative research I'm doing with Micah, as well as with Homiun Karimi, who works here at McMaster University. So for the rest of the talk, I'm going to switch to Beamer slides, and why don't we just, I'll do that now, and we'll get right on with the talk. So here's my cover slide. The title, as you can read, is the Gordon-Litherland pairing for knots and links in thickened surfaces. And for truth in advertising, I should probably remove the links just because I'm not going to say much about how to generalize this to links. The methods I'll talk about do work, but the statements are a little delicate, and I won't bother to state them carefully today. As I mentioned, this talk is based on two joint papers that are in preparation. One is with Micah and Homiun, and one is with Homiun. And a word from my sponsor: this research was supported by a generous grant from the National Sciences and Engineering Research Council of Canada. So background, let me talk about what had been done on these problems before. So Darrell Cooper, in his thesis in 1982, studied signatures of knots in arbitrary three-manifolds. Subsequent work by Mendelbaum and Moishison took that problem up, as well as Chimichoni and Turaev, who studied the problem of signatures in quasi-cylinders. In all of those cases, the knots are assumed to be homologically trivial, which just means that they bound Seifert surfaces. And one phenomena that was studied was that the Seifert surface is not canonically, well, even for classical knots, in S3, it's not canonically determined by the knot, but the signatures of the Seifert surfaces may depend on which Seifert surface you choose. So in the general setting, you have an action of H2 of the three-manifold on the set of Seifert surfaces that you can construct for your knot, and that will be an effective action and can often, or will often, change the signature values that you define. So that speaks to how to generalize signatures to knots in arbitrary three-manifolds. As for generalizing it to virtual knots, two methods have been outlined for doing that. One was a 2010 JKTR paper by M. Lee and Lee, and a second was a more recent article which I wrote jointly with Micah and Robin Gaudreau, which is soon to appear in the Indiana University Journal of Math. In both cases, signature type invariants are defined for not all virtual knots and links, but on subcategories of virtual knots and links. So in the M. Lee Lee paper, they're defined for checkerboard colorable knots and links, and the definition is largely combinatorial. In the paper with Micah and Robin, they're defined for almost classical knots and links, which are knots and links that admit oriented spanning surfaces or Seifert surfaces. And the approach to defining the invariants is the standard one, which I will go over momentarily. So the first goal of the talk is to provide more general definitions of signature invariants for knots and links in three manifolds and for knots and and for virtual knots and links. So in this case of arbitrary three manifolds, we will almost always specialize to thickened surfaces. A second aspect of what I will talk about has to do with generalizing the Gordon-Litherland pairing. And it should be noted that not long ago, Josh Green generalized the Gordon-Litherland pairing to Z2 homology 3 spheres, and he used it to give a beautiful geometric characterization of alternating classical links. This should be compared with very corresponding or close result by Josh Howie, published in the same year. And Josh Green used his approach to give a new proof of the first and second Tate conjectures for classical knots, which is quite appealing. And I should mention on this, an earlier talk in the series, a beautiful talk by Thomas Kindred, talks about generalizing their geometric method to prove the third Tate conjecture, which is largely seen to be the most difficult of the three Tate conjectures. And that's a very intriguing proposal, and it's a highly recommended talk, a really beautiful talk. So a second goal of this talk today is to extend the Gordon-Litherland pairing to more general three manifolds. And again here, by three manifolds, we mainly mean thickened surfaces, and to use it to give a characterization of alternating knots and links in those three manifolds. So let me review how you define the knot signature classically. So this is for knots in S3, or if you would like to think about classical knots as knots in thickened surfaces, they're knots in S2 cross I. There are at least three ways to define the knot signature. The first and the common way is due to Trotter and Morisugi. And in that approach, you use the Seifert surface to construct a Seifert form, which is the linking pairing. It's a form given by linking pairing where you push so the Seifert form on alpha beta is a linking pairing of the push off of alpha with beta, and for our purposes, our convention is to use the negative push off, to push alpha off in the negative direction of the Seifert surface with respect to all the orientations. And any matrix representing theta, so that matrix is denoted V here, but it just represents the Seifert form. If you choose a basis for H1 of F, then you can write the matrix out. That's called a Seifert matrix. It's, of course, well-defined up to unimodular congruence. And the signature of the symmetrized Seifert form, which is the sum of V and V transpose, that will be invariant under unimodular congruence. And more generally, it will be invariant under an operation called S equivalence, which I will refer to obliquely later. So the signature, as it turns out, is independent of the choice of Seifert surface and gives a very useful and powerful invariant for knots, which is denoted here by sigma. And it's just the signature of this symmetric matrix. And just recall, the signature of a matrix is the sum of the positive eigenvalues minus the sum of the number of positive eigenvalues minus the sum of the number of the negative eigenvalues. So a second approach to defining signatures is via four manifolds, and this speaks to the application of knot signatures, which is toward determining concordance properties and sliceness properties of knots, and that's what they're mainly used for, though they also have applications to unknotting numbers. But this approach is due to Kaufman and Taylor, and for that approach, let's view our knot in S3, but view S3 as the boundary of the four-ball. And if you give me a Seifert surface for that knot, we'll call that Seifert surface F, we can push that Seifert surface, or the interior of the Seifert surface, into the four-ball, and we can cut the four-ball along the ciphered surface and form the twofold branched cover branched along F. That will be a four-manifold, and it will be a four-manifold with boundary, and its boundary will be the twofold branched cover of S3 branched along the knot. And notice that that twofold branched cover of the knot, that's a Z2 homology three-sphere, and it's not difficult to see that the associated intersection form, denoted here Q, on the second homology of the twofold branch cover of the four-ball, that's a non-degenerate symmetric pairing. And it has a signature which is equal to the knot signature. So the signature of the knot can alternatively be defined in terms of the signature of this intersection form Q on this four-manifold obtained by the twofold branch cover of the knot. The third way of defining knot signatures, and this is our preferred approach today, is to use the Gordon-Litherland pairing. And here the advantage is we can form the Gordon-Litherland pairing for any spanning surface, whether it's oriented or not. So let F be a spanning surface which may or may not be oriented. And Gordon and Litherland defined a symmetric bilinear pairing on the first homology of the surface. So that's denoted with curly G sub F, and it's defined on the first homology of F, takes integer values, and in the special case when F is a ciphered surface, i.e. when F is oriented, the quadratic form specializes to the Trotter form. And when F instead comes from a checkerboard coloring of the knot, say it's the black or the white surface, then the Gordon-Litherland pairing specializes to the Goeritz form for the knot, or for the knot diagram, I should say, because the Goeritz form is sensitive to the diagram. It's not a knot invariant a priori. So in this way, Gordon and Litherland simultaneously generalized the Murasugi-Trotter form as well as the Goeritz form. So let me give a few more details about the Gordon-Litherland pairing. So first, if you choose a tubular neighborhood of your surface, F, and let F tilde be the boundary of that tubular neighborhood, N, then F tilde will be a twofold branched cover. Sorry, just a twofold cover, not branched, excuse me. And F tilde will be connected precisely when the surface, the spanning surface here, F, is not oriented. So associated to that setup, we have the transfer map, which is a map from H1 of F to H1 of the twofold cover. And roughly speaking, it just doubles if you represent an element in first homology by a simple closed curve. It simply takes the push off of that curve in both directions. So it doubles that curve. And the Gordon-Litherland pairing, G sub F, is defined by taking the linking pairing of that transferred curve with beta. So what I'm trying to say is this formula here. That the Gordon-Litherland pairing on alpha beta is just the linking pairing of tau alpha with beta. So it's very similar to the ciphered, the standard ciphered approach. Just you take instead of taking the negative push off, you push alpha off in both directions at the same time. The price you pay for using the Gordon-Litherland pairing is that you need a correction term to account for the fact your surface may not be oriented. And the correction term is denoted E sub F here, and it's an Euler number for the surface, and it's defined precisely or computed precisely as minus the linking number of the knot with a push off of the knot, and you choose the push off K tilde here. you push it off so that it misses the surface, and that determines a longitude of our knot, and then we can take the linking number of that longitude with k, and that's our Euler number. In the special case, when f is oriented, then the Gordon-Litherland pairing coincides with the symmetrized Seifert pairing, and this correction term, E sub f, is equal to 0. So a theorem due to Gordon-Litherland proved in 1978 is that this pairing is symmetric and bilinear, and that the knot signature can be recovered as the sum of the signature of the Gordon-Litherland pairing plus 1/2 times the correction term. So this gives a very useful formula for the signature and an efficient way to compute it. So let me outline the simple algorithm you get for computing the knot signature using a checkerboard surface associated to the checkerboard coloring. So in what I'm going to talk about, I'll come back to checkerboard colorings again and again today, and throughout I will consider the black surface as the preferred surface on which to compute signatures and other knot invariants. So given a checkerboard coloring, let's let f be the spanning surface obtained from the black regions. So it's obtained by taking the union of all the black disks along with half-twisted bands, which are attached to crossings and join the two black regions. If we enumerate the white disks x0 up through xn, then they give a system of generators for the first homology of the checkerboard surface. And they're sort of the boundaries of their curves that go around the holes in that surface in some sense. And for each crossing, I want to define an incidence number to be, it will equal plus or minus 1, depending on the crossing and the coloring at that surface. And it will be plus 1 if the crossing looks like this, and negative 1 if the crossing looks like this. So this is standard, and maybe I'll make a point, which is a useful observation, which is if I have a simple closed curve on the surface, say it's a generator for first homology, maybe it's a gamma curve, that goes through that crossing, then eta predicts or computes the self-linking number gamma would have in the Gordon-Litherland pairing. So if you push gamma off in both the positive and negative direction, and you take the linking number of tau gamma with gamma, you'll see that it's equal to eta. And interestingly, it's independent of which way you orient gamma. So that self-linking number will be plus 1 whether gamma goes through the crossing from the top or from the bottom. And it works also for this one. So if my gamma curve goes through crossing like it is on the right-hand side with eta equals minus 1, then the linking pairing of tau gamma with gamma will be negative 1. So the Goeritz matrix is constructed by this formula. So it's a sum over crossings that are incident to both xi and xj, and it's a sum of minus the eta invariance of those crossings, and the diagonal entries are equal to this. It may look like a somewhat complicated formula. It's just arranged so that the sum of the entries along the rows are all equal to 0. So we get a big matrix. If we do this for all I and j, we'll get an n plus 1 by n plus 1 matrix. However, the boundary of x0 is a linear combination in h1 of f of the boundaries of x1 through xn. So if we remove the first row and first column, we get a basis for H1 of F, and the Goeritz matrix is just the associated matrix you get from these formulas up here with the first row and first column removed. And it represents the Gordon-Litherland pairing. So in particular, the signature of Litherland pairing is equal to the signature of the Goeritz matrix. Allows us to compute the not signature as the signature of G plus 1/2 E of F, just as before. Now, before I go on, I should mention that there are two other sets of invariants you can get from this setup. Well, really for knots, there's only one other invariant you get, which is the knot determinant. So you also get that the determinant of the knot, usually defined in terms of Alexander matrices, or evaluating the Alexander polynomial at -1, this determinant can alternatively be expressed as the absolute value of the determinant. Well, it's really any matrix representing the Gordon-Litherland pairing, but I'll write it as the determinant of GF. So, and for links, for classical links, invariants, which are modes, or the dimension of the zero-dimensional eigenspace of the Gordon-Litherland pairing. So here we get that also the knot determinant is given by the absolute value of the determinant of the Goeritz matrix. Okay, so we have all these invariants arising. And there's a simple formula for the correction term. So if you notice here, we need, once we have the Gordon-Litherland matrix, we can certainly compute its signature, but we're still left with computing the correction term, and there's a simple formula for the correction term in terms of the crossings and their etas, their incidence numbers, and that formula is given by this relation, which tells us that the Euler number of the surface is -2 times mu of k, where mu of k is the sum of the incidence numbers. And one observation here is the type 2 crossings depend both on the orientation of the knot as well as on the checkerboard coloring. But type 1 crossings are one for which the black surface is consistently with the Seifert smoothing. This crossing would be a perfectly acceptable oriented smoothing in a Seifert surface for my knot, whereas this on the right would not be. You can see that the orientations on the arcs reverse there. Okay, so for the next bit, I'd like to discuss how to generalize the Gordon-Litherland pairing to knots and thickened surfaces. So henceforth, we'll call sigma sometimes the Carter surface, but it will be a compact connected oriented surface, and we'll take a knot in sigma cross I and see if we can use the generalize the Gordon-Litherland pairing and use it to sigma determinant invariants of knots. And as I mentioned at the beginning, with more effort, you can prove this hold more generally for links in thickened surfaces. And I won't go into details on that, but it's fairly standard. The first thing you need to do, or the first thing to say here, is to make it clear what I mean by the linking pairing for knots and links in thickened surfaces. And this is a bit different from how it is for classical knots. So what we get is an asymmetric linking pairing. So given two disjoint knots, J and K, in sigma cross I, we'll define the linking number of j with k to be the intersection of j with any two chain, B, which bounds the knot relative to sigma cross 1. So it can have another term in the boundary that lies at the top of my cylinder. So in practice, this linking number counts the number of times that j passes over k, and it counts those with sign given by the writhe of the crossing. And here, above and below are determined by the positive I direction in sigma cross I. So throughout this, I'm going to use P to denote the projection map onto the first coordinate of sigma cross I. And let's assume that F is a spanning surface for a knot in sigma cross I. We'll define the Gordon-Litherland pairing relative or for that surface using this asymmetric linking pairing applied to the transfer map of alpha with beta, and then subtracting off this term p star alpha dot p star beta, and here p star is the induced map on H1, and dot is just the regular intersection, algebraic intersection number of curves in H1 of sigma. So with this definition here, it's fairly routine to prove that the associated pairing is symmetric. Further, it's not difficult to write out a correction term which yields a signature type invariant for knots in thickened surfaces. Let me take a moment to describe to what extent that signature type invariant really is an invariant of knots and links in thickened surfaces. That's the interesting part. So for this, I want to introduce the notion of S star equivalence. And S star equivalence is an equivalence of spanning surfaces that includes ambient isotopy, attaching or removing a one handle, that the A and B would be what you would get for just regular S equivalence, and the additional move is attaching or removing a small half-twisted band as either twisted in a left-handed way or a right-handed way. And notice that if my surface, the shaded part here, if that was oriented, then after attaching this half-twisted band here, it would no longer be oriented. So this third move takes me out of the world of oriented surfaces. And here's some interesting facts. First fact is every classical knot admits a spanning surface. If you want, you can see this because every classical knot is checkerboard colorable, and you could use the black surface, for instance, as a spanning surface. Furthermore, less obvious but still true is the fact that any two spanning surfaces for a classical knot are S star equivalent. So we'll come back to this, but this was proved first by Gordon and Litherland in their paper. And lastly, and most interestingly, this third point is neither one nor two is true in the general context of knots and thickened surfaces, at least not when the surface has genus 1 or more. So what we can prove is if we take the correction term and define it just like we did before. So the correction term is the Euler number, which is given by the linking minus the linking of K with the push-off that misses the surface. Then any two S star equivalent spanning surfaces will have equal corrected knot signature. So this formula, signature of the Gordon-Litherland pairing plus 1/2 Euler number, that's our corrected or our corrected knot signature formula. So this lemma is saying that the knot signature is essentially well-defined up to S star equivalence for knots in thickened surfaces. As a corollary, so if we define the knot signature of K relative to F by this formula, it's well-defined and depends only on the S star equivalence class of the surface. A further observation is if our spanning surface is oriented, then just as in the classical case, the correction term is 0 and the signature is equal to the signature of the Gordon-Litherland pairing on the nose. Furthermore, that Gordon-Litherland pairing is equal to the symmetrized Seifert matrix on the nose. So this recovers the signature formulas that you get in the case of almost classical knots. So you can use this same approach to define determinant and nullity invariance of knots in thickened surfaces. So the determinant of the knot relative to a given spanning surface F is the absolute value of the determinant of the Gordon-Litherland pairing, and the nullity is just the nullity of the Gordon-Litherland pairing. It's just the number, the dimension of the zero-dimensional eigenspace. And just as you do with the knot signature, the determinant and the nullity are both invariants of knots. They depend on the choice of spanning surface, but only on its S star equivalence class. So here's a nice example. It's an alternating knot with, so it's an alternating knot on the torus. So we're going to imagine identifying the torus, but identifying the sides, the left and the right sides, and the top and the bottom in the usual way. And when you do that, you get a knot with 3 crossings, and it's checkerboard colorable. In one coloring, the black surface is drawn here, and in the other coloring, it's the roles of the black and the white surfaces switch. And we can use the Gordon-Litherland approach to compute the signatures for those 2 spanning surfaces of this same knot. So let's let F be the spanning surface for that in that coloring, the dark surface or black surface, and let's let F star be the black surface on the right-hand picture. So the F star is, we'll call that the dual surface to F. So using the alpha and beta curves here, we can compute the Gordon-Litherland pairing, and it's fairly simple. It's not hard to see that they are generators for H1 of F, so they give a basis for H1 of F. It's also pretty easy to observe that alpha goes through 3 crossings, 1, 2, 3, and each of those crossings has eta equal to -1, so the self-linking of alpha is -3. Likewise, beta goes through that same crossing once. That crossing still has eta equal -1, so beta has self-linking number -1. And then last, it's a little bit tricky to see, but if you draw what happens in the band as alpha and beta go through here, you'll see that alpha is above beta, so it's positive or it's two-sided push-off. Both of them lie above beta, so that would count. Because alpha crosses over beta as a negative crossing, that would count -2, and we need to subtract the algebraic intersection of alpha and beta, and the algebraic intersection is -1, and so -2 minus -1 is -1, and that gives me the off-diagonal entry. And then this last entry is also equal to -1 by virtue of the fact this is a symmetric matrix. So the Gordon-Litherland matrix is given by this 2 by 2 matrix here. You can also compute that 2 of the crossings here are type 2 and 1 is type 1. The 2 crossings of type 2 both have eta equal 1. So the mu of k is, they both have eta equal -1. So mu of k is -2, or the Euler number is -2 times -2, which is 4. So in any case, the knot signature is given by the signature of this matrix plus 1/2 times this. And of course, this matrix has signature, let's see, that entry is negative, so it has 1 negative eigenvalue. Its determinant is equal to 2, so it actually has 2 negative eigenvalues. So the signature of this matrix is -2, and the knot signature is therefore -2 plus the correction term, which is +2, or 0. And the determinant is the absolute value of the determinant of this matrix, which is 2. Okay, so that tells me how, so this picture is telling me how to compute those two, whereas this picture determines this computation here. So let me go through that. In that picture, we have 3 basis elements, alpha, beta, and gamma. And you'll note that alpha and beta do not intersect, so that means the off-diagonal entry here and here are both 0. Alpha and beta both intersect gamma, but they only intersect it in a sort of flat open part of the curve, nowhere near a crossing. And you can see that the positive and negative, or the 2 push-offs of alpha, one will be above gamma, the other one will be below gamma, and it will cancel when I subtract off p star alpha dotted with p star gamma. So that's what tells me these other 2 entries are 0. And last but not least, alpha goes through 1 crossing, and that crossing has eta equal +1. Beta goes through 1 crossing, also has eta equal +1, and gamma goes through 1 crossing with eta equal +1. And that tells me that these 3 diagonal entries are all equal to 1. So as it turns out, the Gordon-Litherland pairing is represented in this basis by the identity matrix, the 3 by 3 identity matrix. When you switch from a surface to its dual, you the type of the crossing and the eta invariant switch. So in this new surface, we have 1 type 2 crossing, and it has eta equal to -1. It has eta equal to +1. Anyway, my Euler number, it turns out, is -2. So the signature from this point of view is the signature of this matrix, which is 3, minus 2 divided by 2 is my correction term, so -1, which is equal to 2. And the determinant is just the determinant of the absolute value of the determinant of that matrix, which is equal to 1. Okay, so that's all to say that, so that's how this calculation is carried out. So let me return to spanning surfaces and what we can say about their existence and uniqueness in the general case of knots in thickened surfaces. So as you will remember, for classical knots, or knots in S2, spanning surfaces always exist, and they're unique up to S-star equivalence. This fact was originally proved by Gordon and Litherland, but it's written up with a nice and simple combinatorial argument by Yasuhara in 2014. in the more general case where you consider knots in sigma cross I, where sigma is a surface different from S2, the situation's more complicated. You don't generally have existence, and you also don't have uniqueness up to S star equivalence. Instead, for existence, we have the following proposition, which is a knot in a thickened surface will admit a spanning surface if and only if that knot is homologically trivial as an element in the first homology of my surface with Z2 coefficients. Okay, so this is a fairly self-evident proposition. And in either case, 1 or 2, which are equivalent by this proposition, in either case, the knot will admit a spanning surface if and only if that knot is checkerboard colorable, meaning that we can color, it's represented by a checkerboard colorable diagram, one which admits one that can be colored black and white so that each edge bounds two regions of different colors. So no white region bounds a white region and vice versa for black. So as for uniqueness, if you give me a knot C, and if we use F to denote the black surface and F star to denote the dual surface or the white surface, then when the genus of the surface is positive, these two black and dual surfaces will not be S star equivalent. And in fact, so what do we know? We know that any two surfaces, F1 and F2, any two spanning surfaces for my knot, if they're S star equivalent, then they will represent the same homology class in the second relative homology of sigma relative to my knot. Furthermore, we know that any spanning surface is going to be S star equivalent to either the black surface or the dual surface. And in general, unless sigma is a two-sphere, the black surface and the dual are not going to be S star equivalent. So what does this mean for us? Well, this means that the signatures, determinants, and nullities are really going to be able to take on two possible values depending on which S star equivalence class we choose for the knot. And you see that in practice. I mean, we already saw that, the signatures and determinants were different for the two spanning surfaces. And the purpose of this lemma is to say, well, that's actually all there is. These results apply to virtual knots, and I'd like to take a moment to talk about those applications. And let me just briefly recall the history and definitions of virtual knots. So they were introduced by Kaufman in 1999, though the definition dates from a much earlier talk he gave. And he defined virtual knots as equivalence classes of virtual knot diagrams by what are called generalized Reidemeister moves. They have alternative formulations, and the one most useful for us is a formulation given by Carter Kamato in a 2002 JKTR paper, where virtual knots were seen to be equivalent to stable equivalence classes of knots in thickened surfaces. So stable equivalence here refers to isotopy of the knot in the thickened surface, diffeomorphism of the thickened surface, carrying the knot to possibly a different knot, a knot in a different isotopic class, as well as addition or removal of one handles and multiple removals of one handles, the only requirement being that the one handles be disjoint from my knot or its projection. So a knot is said to be minimal if it is not isotopic to one that admits a d-state. And Kuperberg showed that for a virtual knot, or more generally, any minimal representative is unique up to diffeomorphism of the spanning surface. So in particular, the genus of that surface is unique invariant associated to virtual knots, and that is sometimes called the virtual genus. So the virtual genus of a virtual knot is just the genus of a minimal representative. Now, if you give me a knot in a thickened surface, I can project the knot, and I can ask if, well, I'll generally assume that the decay is a regular map, so it's a regular immersion, so it has at worst double points, but otherwise it's one-to-one. And I can ask whether sigma minus the image of k, how the complement of that graph in sigma decomposes. And if all of the components of sigma minus p of k are two disks, then we'll say that that knot is cellularly embedded. Virtual knots, it is a known fact that you can always represent them by cellularly embedded knots in thickened surfaces. And a knot in a thickened surface is necessarily cellularly embedded in order for it to be a minimal genus representative. But not all cellularly embedded knots in thickened surfaces are minimal genus representatives of their virtual knots. Okay, so this is a necessary but not sufficient, cellularly necessary but not sufficient condition for a knot to be a minimal genus representative. This theorem the virtual genus, and it says that if the knot is cellularly embedded and checkerboard colorable with a given coloring, if the determinant of the knot with respect to both the surface F and its dual, if both of those determinants are really a minimal representative for its virtual knot. This is useful because it allows us to detect when we have a minimal representative, and the signature invariants, by the way, and the determinant invariants then become invariants of the underlying virtual knot. And that's because we use Kuperberg's theorem. And I guess I should point out the sort of fly in the ointment in this approach to defining invariances is we cannot prove, because it is not true, we cannot prove that this is invariant under stabilization. So stabilization is a move that unfortunately wrecks our invariants. Our invariants are not unchanged under stabilization. The way we fix that is we appeal to Kuperberg's theorem and we apply the signatures and nullities and determinants only to minimal representatives. However, in doing that, we need to authentically know when is a minimal genus representative for the virtual knot and link, and this theorem plays that role for us. So this is a useful theorem in applying. A second interesting result that has to do with the action of H2 on the signature invariants. And if you go back to the results of and Chimashoni and Turayev that I talked about earlier, we know that there's an action of the Seifert surfaces, and that action can change the signature invariance. And typically that action for knots in a thickened surface, H2 is a copy of Z, and so we have a Z's worth of different Seifert surfaces or span you could choose. So you would expect a whole infinite number of signature type invariants. And what we see is that we can compute both of the signature type invariants from one single surface. So let's see how that works. So one way, the way that H2 acts of H2 of sigma, and that's a parallel copy of the surface, and you attach it to your spanning surface by a thin tube. And when you do that, you'll get a new spanning surface for your knot. And that new spanning surface is denoted F prime. F prime will be S star equivalent to the dual surface to F. So it's not equal to F star, but it is S star equivalent to F star. And the Euler number of this new surface, F prime, is identical to the Euler number of F. And this fact holds because the two surfaces have the same local behavior near the knot. And that Euler number is determined entirely by the local behavior of the surface near the knot. So if you give me a spanning surface for a knot, call it F, and let's assume further that the inclusion map induces a surjection on H1. So this inclusion map here will induce a map on H1, and I'm going to assume that's surjective. Note that this condition always holds when K is checkerboard colorable and F is the surface, and K is assumed cellularly embedded. In that case, let's call curly K, let's set that to be the kernel of the map from H1 of F to H1 of sigma. So the theorem states that then the signature of F prime is equal to the signature of F restricted to K. Okay, so this is not an obvious fact, but it is true, and it's proved by relating these two matrices, the Gordon-Litherland pairing of F to the Gordon-Litherland pairing of F prime, and showing that with a copy of what I call the Carter surface, then that amounts to adding a term which cancels with something perpendicular to this. So I'll prove this, but I don't think I have time for that. A similar statement to this holds for the not determinant and the nullity. And the use of this result is that it allows computation of both sets of invariants using the same surface. As a remark, the hypotheses in this theorem are always satisfied when K is cellularly embedded in checkerboard colorable. Well, it's always satisfied by the surfaces, the black surface and its dual. So as an example, consider this this knot, four-crossing knot in the torus. So again, I'm going to assume that I'm identifying the top and the bottom of this square in the usual way, and the two sides, left and right, in the usual way to create a torus. And this knot, you can see, bounds an oriented surface or a ciphered surface, and moreover, that surface is the span also genus 1, and it has two generators. H1 has two generators, alpha and beta, drawn here, and alpha has a curve on the surface. It goes through two crossings, both with eta equal. So alpha has self-linking 2. Beta likewise goes through two crossings, both with eta equal +1. So it has self-linking 2. And then it's not hard to see that the Gordon-Litherland pairing of alpha or of alpha with beta, which is really the linking number of tau alpha with beta minus the intersection of alpha with beta, it's not hard to see that that's equal to 0. So those two off-diagonal terms are 0. Of course, has two positive eigenvalues, so its signature is 2. And note that because this is an oriented spanning surface, the correction term is 0. Maybe I should write that down. E of f is 0 here. As well, the determinant is equal to 4, which is just the absolute value of the determinant to that matrix. Okay, that's a pretty easy calculation. To calculate for the dual surface, one way would be to switch the colorings and write down all the generators and do a similar computation, but it's actually, if you notice, the spanning surface here was a genus 1 surface. The background surface, or Carter surface, is also genus 1. The alpha and beta curve are the two standard generators. So the kernel, so remember, K here, script K was the kernel of the map from H1 of F to H1 of sigma cross I. In this case, that kernel is equal to 0. Trivial matter to see that the associated signature invariance is 0 and determinant is equal to 1. As a corollary, we can use the chromatic duality theorem to relate our signatures defined using the Gordon-Litherland pairing to the combinatorial signatures defined by M, Lee, and Lee, as well as to the determinants and nullities they defined using the Goeritz matrices. So, and the interesting part here is that they're not, but in fact, the Gordon-Litherland signatures, nullities, and determinants are for one surface are equal to the M, Lee, Lee signatures, determinants, and nullities using the dual, using its dual. The interesting part here is we'd expect these to be equal, the Gordon-Litherland and Goeritz matrices, to have the same kinds of invariance of knots, just like it is in the classical case. But in fact, you need to switch the surface you use for the Gordon-Litherland pairing with its dual when you use Goeritz matrices. Okay, so that's a subtle from the classical case. So to end the talk, I'd like to give an application to alternating virtual knots. And one useful fact observed by Neko Kamada is that all alternating virtual knots, while they required an assumption of checkerboard colorability to apply in the general context, they work whenever a virtual knot is alternating. I guess I should maybe pause for a second and say what an alternating. Two ways to define this. When your virtual knot is represented as a diagram, then we say that diagram is alternating if the classical crossings alternate between over and under as you go around, ignoring virtual crossings. Alternatively and equivalently is alternating if it in a thickened surface. And its knot is then the incidence value of every crossing will be the same. So with regard to the checkerboard coloring. Now, whether it has incidence number +1 or -1 will depend on how you choose the black surface and the white surface. And our convention will be that we choose the coloring incidence equal to -1. When you, next theorem is just the observation that if you take an alternating diagram on a surface, coloring, which you know exists by this fact, and associate to it its black and white surfaces, the W here, then the Gordon-Litherland pairing associated to those two surfaces, GB and GW, will both be definite and they will have opposite sign. So one will be positive and one will be negative. And if you follow our convention where you make all the incidence numbers equal to -1, then the black surface will be negative definite and the white surface will be positive definite. For both of those surfaces, notice that definiteness means that the determinants are not equal to 0 for either the black surface or the white surface. So what that implies as a direct corollary is that alternating virtual knot diagrams have minimal genus. Useful observation. And as the last result I'd like to talk about today, it's a converse to the previous. So in this theorem here, we saw that the black and white surfaces are definite and of opposite whenever you have an alternating diagram. And this says that whenever you have a checkerboard colorable knot in a thickened surface who admits a positive and negative definite spanning surface is alternating. So this gives a converse to that theorem. And it is the analog for knots in thickened surfaces of this very useful and beautiful characterization of alternatingness for classical knots, Green and Howie. So that ends my talk. Here are some references. So the first is a paper that's in preparation with Micah and Homian. It outlines the Gordon-Litherland pairing and how you can use that to define signature invariants for knots and thickened surfaces, for links and thickened surfaces, as well as for virtual knots and links. A second reference here is a paper with Homian Karimi, which discusses this last characterization, links and thickened surfaces, and that was recently posted on the archive. And last but not least, Homian Karimi's PhD thesis is a very comprehensive treatment of alternating virtual knots. It is available online through the McMaster online library service, or you can find it as well on my posted on my web. And it discusses some of those much further and discusses homology of alternating virtual knots and links. So to close, I'd like to thank everyone for their attention and for tuning in, and hope you're all doing